Do you remember the definition of the hyperbolic functions? Well, if you don't remember them, they're right there on the screen. So you might recall that we defined hyperbolic sine to be e to the x minus e to the negative x over 2. Hyperbolic cosine was e to the x plus e to the negative x over 2. And then tangent, cosecant, secant, and cotangent we defined as ratios of those functions in the correct format. All right? So hyperbolic sine and hyperbolic cosine are defined in terms of e's. That was the important thing. And then we had a whole bunch of properties that we talked about. A whole bunch of identities that look an awful lot like trig identities. I don't think I went through all of these before break, but I definitely know we talked about the equivalent of the Pythagorean identities in various formats. And I think I talked about the sum and difference identities, how they're very similar to the trig identities. And then, of course, we did some calculus. We had some derivative rules and some integral rules. And we saw that these worked really nicely for sine and cosine. The derivative of hyperbolic sine was hyperbolic cosine, and the derivative of hyperbolic cosine was hyperbolic sine. Unlike sine and cosine, we had to worry about which one had the negative and which one didn't. Don't have to worry about these here. No negative signs at all. So the integrals work out exactly the same also. But we did have some differences with our pluses and minuses later on. The derivative of hyperbolic tangent was hyperbolic secant squared, which is the same. But the derivative of hyperbolic secant turned out to have a minus sign in front of it. If you're dealing with just a regular trig functions, you don't get the minus sign there. So there were some slight differences in our derivative rules. Questions about any of that? That's kind of where we left off the other day. Well, a week and a half ago. Are the hyperbolic functions one-to-one? Some of them are, that's correct. For example, hyperbolic sine is one-to-one, but hyperbolic cosine is not. Hyperbolic tangent is. Cosecant is. Secant is not. Cotangent is. Well, so these four, we're guaranteed that these four have inverses, aren't we? These two don't, but what do we do to make it so they have inverses? We bound them. So this one we would bound. How would you bound this one to make it one-to-one? You could either use the positives or you could use the negatives. Which one do you like? Typically we use the positives. So you would bound this one from 0 to infinity, and I think this one the same thing. Bound it from 0 to infinity, and then they would have inverses. All right, so we have definitions of the inverse hyperbolic functions. Oops. Somewhere. Here they are. Here are the definitions. I'm not going to write them all down. They're here in your book. What shouldn't surprise you is that all these definitions involve ln. Why should that not surprise you? How did we define hyperbolic sine to begin with? It was defined in terms of functions of e. What's the inverse of a function with an e in it? A natural log. So it should be of absolutely no surprise that the hyperbolic inverse functions are all defined in terms of ln's, because the hyperbolic functions were all defined in terms of e's. And then you might notice this one has the limited domain because it wasn't one-to-one. This one also has the limited domain because its inverse was not one-to-one. Why does that one have a limited domain? You don't want to get 0 on bottom. Correct? So I don't want to use 1 and -1. That would give me 0 on bottom. That would be bad. How come I can't use, say, 2? What's wrong with 2? It would give me a negative in here, wouldn't it? 1 plus 2 is 3. 1 minus 2 would be -1. Can I do ln of a negative number? No. So that's why that one has to have a limited domain. You could also see it in the original graph. If you look at the graph of the hyperbolic tangent, its range is limited to -1 to 1. Since the range of hyperbolic tangent is limited, the domain of hyperbolic tangent inverse is going to be limited. That's a big function, isn't it? Hyperbolic tangent inverse. That's a lot to say for one little function. All right. Anyway, so there's our definitions. Could you now take the derivative of all those functions? I think so. Because if hyperbolic sine inverse of x is defined to be ln of x plus the square root of x squared plus 1, could you take its derivative?
You can't see it.
Makes it easier if you can see. How do you take the derivative of ln of x plus the square root of x squared plus 1? How do you take derivative of ln of something? 1 over the something. And then we have to use the chain rule, and we have to multiply by the derivative of it. So what's the derivative of x plus the square root of 1 plus x squared?
Plus 1/2 x squared plus 1 divided by 1/2 times 2x.
Very good. So yes, we can find the derivatives. Because they're all defined in terms of ln's. We know how to take derivatives of things that have ln's in them. But the bigger question is, can you simplify that? The 2's cancel. Absolutely they do. 2's cancel out. They multiply to be 1. Any other good ideas?
Would it be x squared plus 1 negative 1/2 and then the rest on the bottom equal to?
Not quite, because you're on the right track though. This one is 1 over x plus the square root of x squared plus 1, and then we would have times, right, we'd have 1 plus x over the square root of x squared plus 1. And so if we wanted to multiply, we'd actually have to do a distributive property, wouldn't we? Any other good ideas? Don't simplify it. It actually simplifies down pretty nicely. And I think this is the way to do it. We're going to find out, see if I can get the right answer here.
Did you get a common denominator in the parentheses or no? You can't do that.
I could do that. I could get a common denominator here and then add and see what I have and then multiply. That might be a good idea. But I'm going to try something different. I don't know if this is going to work or not. We'll find out. I didn't plan this in advance. 1 over x plus the square root of x squared plus 1. I'm going to take this and I'm going to multiply top and bottom by x minus the square root of x squared plus 1. What's that? That's the conjugate. I'm going to multiply top and bottom by the conjugate. And then, of course, I still have all this other stuff over here. 1 plus x over square root of x squared plus 1. let's see if that helps at all. I have x minus the square root of x squared plus 1 divided by, what do I get on bottom? X squared minus x squared plus 1. So it would just be negative 1, wouldn't it be? Run that minus sign through. Times 1 plus x over square root of x squared plus 1. So this is, you said this was a negative 1. So that's going to be negative x plus the square root of x squared plus 1 times 1 plus x over the square root of x squared plus 1. Now what? Any good thoughts? Well, let's just go ahead and do FOIL here. What's negative x times 1? Negative x. What's negative x times that? Negative x squared over the square root of x squared plus 1? Plus square root of x squared plus 1. And then what's square root of x squared plus 1 times x over the square root of x squared plus 1? X. All right, so it's getting better. Those add up to 0, don't they? All right, so last step. Let's now get that common denominator that people talked about before and add those together. That's negative x squared over square root of x squared plus 1 plus, I've got to multiply top and bottom by square root of x squared plus 1. What happens when I multiply the top by square root of x squared plus 1? I get x squared plus 1. Finally, when I add my fractions together, what do I end up with? 1 over square root of x squared plus 1. So that ugly looking derivative from the beginning did simplify down to be something not too ugly. Not too bad. Alright, so I have a question for you. See how good your memory is. What was the derivative of sine inverse? I think you got an extra negative in there. The derivative of sine inverse was 1 over square root of 1 minus x squared. And the derivative of hyperbolic sine inverse is very similar, except you got a positive in there instead of a negative. So again, all the patterns, all the similarities keep showing up. All right, well, I'm not going to work through all the rest of them. I'm just going to show you the answers. What they're doing in the book here is they're giving you what the chain rule would be. So if this was not just the letter x, then the derivative of hyperbolic sine inverse would be the derivative of whatever's in there divided by square root of the thing squared plus 1. So we had 1 over square root of x squared plus 1. They had this u prime and this u. They're showing you the chain rule. The derivative of hyperbolic cosine inverse turns out to be very similar, except instead of x squared plus 1, you're going to end up with x squared minus 1 down on bottom. What was the derivative of regular old cosine inverse? Looked a lot like this one. It had a minus sign in front of it. So kind of the same idea. The minus sign switches. This one was the plus, this one was minus. The derivative of hyperbolic tangent inverse turns out to be 1 over 1 minus x squared. What was the rule for derivative of regular old tangent inverse? 1 over 1 plus x squared. So again, the rules are very, very similar. And on. You can see the derivative of hyperbolic cotangent inverse, hyperbolic secant inverse. For regular old hyperbolic secant, we had u squared minus 1 in there. Now we have 1 minus u squared.
Is tangent and cotangent the same?
The derivatives of hyperbolic tangent inverse and hyperbolic cotangent inverse turn out to be exactly the same. Yes, they do. Unusual, but it works out that way. Yep. Of course, as soon as you have derivative formulas, you go backward, you have integral formulas. And again, you might remember we had formulas very similar to this before. For example, we had a formula that said the integral of 1 over the square root of a squared minus x squared was, anybody remember what that formula was? That was our sine inverse. So when we had a squared minus x squared, we got sine inverse. What happens when we have x squared minus a squared? That's a fancy way of writing hyperbolic sine or hyperbolic cosine, depending on which one you want. When it's x squared minus a squared, you get the minus there, that's the hyperbolic sine inverse formula. If you have x squared plus a squared, you have the plus there, that's the hyperbolic cosine inverse formula. So again, the formulas look very similar. When we had a squared plus u squared, we got inverse tangent. When we have a squared minus x squared, we get inverse hyperbolic tangent. And this one is very similar to our inverse secant formula, except we have a squared plus or minus u squared before we had u squared minus a squared. Actually pretty much the same thing. Questions on any of those? All right, so let's jump to the homework problems. So, for example, number 66. This is on page 391. Number 66 says y equals hyperbolic tangent inverse of x over 2. Find the derivative. What would you do? What's the formula for derivative of hyperbolic tangent inverse?
We need a chain rule of it.
You need a chain rule of it because you have the x over 2, you don't have just x. But you still need to know that formula, don't you? So what do? Flip back a couple pages. There it is. You look it up. So according to this, we have x over 2. So we take the derivative of x over 2. The derivative of x over 2 is 1/2. And then we divide by 1 minus the original thing squared. So it's 1 minus x over 2 squared. There's your answer. Questions on that? Are you expected to memorize all those? Heck no, you're not expected to memorize all those. You will be allowed to have a little formula card for your next test also. You do not need to memorize all those.
Are you going to have 8 by 11 for the final?
8 by 11 for the final. We'll talk about final, what we're going to do for it. It's a long way away. You don't have to worry about that yet. All right, how about 72? We have y equals hyperbolic secant inverse of the cosine of 2x. And they give us a domain. The domain is between 0 and pi over 4. For purposes of finding the derivative, you don't really need to worry about that. All that is to make sure that our hyperbolic secant inverse is defined, because the hyperbolic secant inverse does have a limited domain. All right, so we find our derivative. Y prime is. Well, once again, we need a chain rule, don't we? Because we have hyperbolic secant, we don't just have x there. All right, so once again, we flip the page back. We look up our rule. It's the derivative minus the derivative of whatever's inside there. So that's going to be minus, what's the derivative of cosine of 2x? Negative sine 2x times 2. There's a chain rule involved in that too, isn't there? Divided by, then you have your u, which is our cosine 2x, 1 minus our function squared. So we're going to have cosine of 2x, square root of 1 minus cosine squared of 2x. There's our answer. Questions on that? Derivatives should not be terribly difficult. Of course, you might need to use the product rule or the quotient rule with some of these also, but basically you're going to look up the new rules for the hyperbolic inverse, plug them in. What is more difficult? Integrals are more difficult. So let's take a look at some integrals. How about number 75 maybe? Which is the integral of 1 over 3 minus 9x squared dx. What do you do? All right, so you flip back and you try to figure out which pattern it best matches. Basically, we have 3 patterns, 1, 2, 3. Which one is it closest to? Looks like the second one, a squared minus u squared. All right, so we have an issue that we have this little number 9 here. We're not supposed to have a 9. So what are we going to do? Multiply by 9 to get rid of it? What's that?
3x squared.
I could factor a 3 out, and then I'd have a 3x squared there. But I'm still not allowed to have a 3 there any more than I'm allowed to have a 9.
So that's 3x.
Do a u sub. Excellent. U equals 3x. So du is 3dx, which means this becomes 1/3 integral 1 over 3 minus u squared du. Just like we had to do when we did inverse tangent function Sometimes we had to do u substitution. Same thing happens with these inverse hyperbolic functions. Sometimes you have to do u substitutions.
Are we missing another 3 there?
Are we missing another 3 there? I hope not.
Is it 3
You just
minus
did.
9?
Right, this was 3 minus 9x squared. So if u is 3x, then u squared is
I see.
9x squared.
All right.
So that's a u squared right there. So I got rid of that 9 by putting it as part of that 3 there. 3 squared gave me the 9. All right, so that's 1/3. And then I look up my rule here. My rule says 1 over 2 times a. So that's 1 over 2 times, what's a?
3.
Not 3. Square root of 3, because this is a squared in the formula. So a squared is the number 3, so a is the square root of 3. ln, absolute value of a plus u, so that's square root of 3 plus 3x. I'm going to put my x's back in one step here. Divided by square root of 3 minus 3x plus c. Questions on that one? All right. How about number 82? Number 82 has the integral of dx divided by x plus 2 times the square root of x squared plus 4x plus 8. Oops, I don't need a dx because I put the dx on top already. Which of our 3 patterns does that one kind of look like? Looks most like the last one because, well, it's definitely not the middle one, right? Because the middle one doesn't have any square roots in it. I think it looks most like the last one because it's got a square root with some stuff underneath and another x on the outside. This one has a u on the outside. So I don't think it looks like that one because there's no x's outside the square root. All right, so we need to put this one in the form of a squared plus or minus a u squared. And then, I don't know what we're going to do with that x plus 2 yet. This doesn't look like a squared plus a u squared or a squared minus a u squared in here, does it?
That's x plus 2 squared. Maybe not.
Not quite x plus 2 squared, unfortunately, because x plus 2 squared would be x squared plus 4x plus 4, unfortunately. That would have been nice. That would have made life a lot easier, I think. Other good ideas.
Before we completed the square, so it gets moving under.
Before we completed the square to make things the right way under the square root. So what do you think we do here? We complete the square to make things look the right way under the square root. That's exactly right. All right, so I'm going to go off to the side here and complete the square. X squared plus 4x plus 8. That's the same as x squared plus 4x plus, what's the number that I want there? I don't want the number 8. I really want the number
16?
not 16. I take 4.
12.
I divide it by 2. And then I square it. That's 4. So I'm going to add a 4. And then I still have the 8. But since I added a 4, I need to subtract a 4. And then what happens with x squared plus 4x plus 4? That's x plus 2 squared plus 4. And I'm going to switch the order. I'm going to write that as 4 plus x plus 2 squared. Why am I switching the order? Because this has a squared plus or minus u squared. So I'm just making it match the way it is in the formula. All right. right, so this becomes the integral. Lose my book here. The integral of dx over x plus 2 times the square root of 4 plus x plus 2 squared. And how does that help? U is x plus 2. If u is x plus 2, this is a u squared. This is a u. And it fits exactly into the formula, doesn't it? So we just let u equal x plus 2. du happens to be dx, and it works out perfectly. I don't need to worry about balancing out any little number. So it looks like the answer is minus 1 over a. What's a in this case? A is 2, so that's minus 1/2. Natural log. Can't fit them both in here. There we go. Natural log of a was 2, plus the square root of 4 plus x plus 2 squared, divided by the absolute value of x plus 2, plus c. All right, so all those same techniques that we had to do when we dealt with inverse trig functions, all those same techniques apply to inverse hyperbolic trig functions. Quite often, you're going to have to do a u substitution. Once in a while, you're going to get a problem like this where you have to do a complete to square. Questions on that? All right, now here's an interesting fact. Well, interesting to me. I don't know how interesting. You'll find it. When we get to chapter 7, which isn't very far away, by the way, we will develop different techniques for evaluating each of those integrals. So we won't use the inverse hyperbolic functions. We'll use this one. We'll use a process called partial fractions, and these two we'll use a process called trigonometric substitution. So, when I look at these forms, I personally don't have any of these forms memorized. Most of the things in Calc 2 I do have memorized, but these, when I look at these, I think of the techniques in Chapter 7, and that's how I answer those questions. If I were clever and I were to simply sit down and memorize those, it would save me a lot of time every now and then, but that's not the way I tend to do things. I tend to not memorize. I tend to figure stuff out when I need to. So that's me. Questions about that?